All right, welcome to the night class. Today, we're talking about exponential functions. Anybody got any idea what an exponential function is? It's a function
that has an exponent.
that has, what is the exponent?
X.
X, variable. Doesn't have to be X. Y'all got it.
Teamwork.
So, if it has a variable for the exponent, it is an exponential function. Easy enough? This first little real-world application, we're going to come to this in one of our examples here in a second. So, we are going to...
Crap, I wasn't paying attention to my back, coach. I wake you up.
We're going to read this real quick. It says, in recent years, beekeepers have experienced a serious decline in the honeybee population in the United States. One of the causes of this decline is the arrival of varroa mites. Experts estimate that as much as 90% of the wild bee colonies have been wiped out. The graph shows typical honeybee and varroa populations over several months. A graph of the varroa population growth from April to September resembles an exponential curve. So from right here, April to September, the exponential curve, it's always going to look like that. The thing about exponential, when you see something improving exponentially or decreasing exponentially, that means it's doing it really fast. It's either getting really big really fast, or it's getting really small really fast.
So does it like get really big really fast and then like settle down?
No, it just continues to keep getting big, okay? So, this is just an example of one. This is 2 to the x power, okay? 2 to the x power, and the way I graph them, and you basically just have to sketch them. See how this graph goes all the way to 32, okay, right here? I'm not going to make you go all the way to 32. You're just going to, once you start getting big numbers on your table, just stop going that direction. What I do, I always try to make whatever the exponent is, I try to make it 0. Now, I want you to understand what I mean when I say this. If it were 2 to the x minus 4 power, what would make the exponent 0? 4. So I would start with 4. I'm always going to start with what makes the exponent 0. Now, for the problems in our that we're doing, I think the exponent pretty much is just 0 to begin with every time. Okay? But at 0, that gives you a kind of a starting off point. Okay? And then I go up from 0. You plug in 1. Well, first off, you plug in 0. Anything to the 0 power is 1. Okay? Here is why. If you had x to the third divided by x to the third, everybody knows that's what? That's 1, right? Same thing divided by itself is 1. Has been forever. But if you use your exponent rules, you understand why. When you divide like bases, what do you do with the exponents? Subtract them. So this is 3 minus 3, which means that's x to the 0, which means it's 1. Everything to the 0 power is 1. Okay? Not 0. So, 0 power, let me erase that. 2 to the 0 is 1. 2 to the 1 is what? 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. At this point, I wouldn't go any higher. Okay? I'd be, okay, I get it. All right? But then I go back and I go some the other direction. 2 to the negative 1 is 1 over 2 to the positive 1, right? Which is 1/2. 2 to the negative 2. Well, that's 1 over 2 squared, which is 1/4. So basically, you're taking all these numbers we just got and put them on the bottom. You got me? 1/2, 1/4, 1/8, 1/16. That number on the bottom keeps getting what? Bigger. The number on the bottom keeps getting bigger. The number on the top stays what? 1 forever. So, will we ever get to 0? No, you never ever get there. All you do is you just keep approaching 0. So when you connect your dots, okay, do not cross that x-axis, because if you cross the x-axis, that means it got to 0. And it doesn't ever get to 0. Everybody with me? Okay? Now, the ones we're going to do here, let me go back to just regular. Our first example basically says graph the exponential functions y equals 4 to the x, y equals 4 to the x plus 2, y equals 4 to the x minus 3 on the same set of axes. Compare and contrast the graphs. So you just have to graph one per axis. So you're not going to have to, they just want you to graph them all at once here, and we're going to look at how they differ. Okay? First off, 4 to the x, it's this one right here that's in the middle. It's approaching what? 0. Okay? Notice, it keeps getting what? As x gets bigger, it's getting what? Y, the range is getting bigger. Okay? So this is getting bigger really fast. Okay? As long as whatever the number is that you're taking the exponent to is more than 1, it will always be getting bigger really fast. Okay? Now, it could be getting a bigger number going this way, or it could be getting a smaller number going that way. What would make it go down? What kind of 4? A negative, because it's just reflecting. Okay? So if it was negative 4, it'd be going down. Okay? So now it's getting really small, really fast. But when I say small, I don't mean like itty-bitty small. I mean like negative 100 small. Everybody with me? Okay? So, this middle one is here. Notice it approaches 0. This one, just like your other transformations and every other function you ever deal with, if you're adding 2 on the outside, how is it moving? Up and down. Okay, it's moving up 2. Okay, what is considered inside in exponential functions? The exponent. Okay, so like on that one I had a minute ago where I had 4 to the x minus 4, that's moving left and right. Everybody with me? Okay, so this number out here, that's always the number that you're approaching. So here, we didn't have anything out there. So notice we're approaching 0. Okay, this one though, right here, we're going to approach what? 2. And we're approaching 2. All right, this one we're approaching what? Negative 3. So it's the same graph, it's just moved down 3. Is everybody understanding that? Easy peasy on the graphing, okay? Long story short, you can't always just put these in your calculator and graph them and get the x and y table from your table.
So that's all we have to do. We don't have to show us doing our x and y.
I do want to see your x and y, yes.
It's just
But you can get it from the calculator is what I'm saying, okay? I do want to see your x, y table and your graph, okay? Part B is the same thing. Oh, is it time? All right, hold on, let me see. So part B, same process. I'm going to go over the transformations really quick. Okay, they're all 1/5, so that means they're going to be, are they getting bigger? Are they growing? Or are they decaying? Decaying, again, because 1/5 less than 1. Okay, so they are decaying. So on this one, if you notice, your graphs go in the opposite direction because it's getting closer to 0 as x gets bigger. Does that make sense? Okay, so what does multiplying by 6 do? What transformation is that? Multiplication. Say it. Nope. I thought you were going to say something else. Yes, but what do we call the dilations? Stretches or shrinks or compresses. Or okay. So that's since it's on the outside, a vertical stretch by 6. This one would be a vertical stretch by 2. And what does the negative do? Reflection. Okay. And again, it's on the outside. So reflecting up and down, we go across the x-axis. So as you can see, y'all listen. As you can see, it's the same graph. It's just been reflected down under the x-axis now. Does that make sense? Okay.
So all we are really doing right now is just adding the exponent.
Correct.
To what we've already done.
Yes. You know about all these transformations. You're now just using them on exponential functions.
That's easy.
It is. Okay. That's the same. Once you get the transformations and everything, you can do any function that's thrown your way. Okay. All right. Example 2, we're not going to spend too much time on it, simply because it's a big word problem that's not really a word problem. All right? Play. All right. according to Newton's law of cooling, there is a law for cooling. Did y'all know that? There is. Like if you take it out of the oven and just sit it on the stove or on top, there's a rule that will tell you how fast it gets cool. Okay, so you don't, when you have your hot chocolate, you don't burn your esophagus. Yes, it melts the cake. Yeah, I know what you're talking about. Yeah.
I need to know the law because I always melt.
The law, yeah, seriously. All right, so according to Newton's law of cooling, the difference between the temperature of an object and its surroundings decreases in time exponentially. So it's getting cooler real fast, okay? It says, suppose a certain cup of coffee is 95 degrees Celsius, and it is in a room that is 20 degrees Celsius. The cooling for this particular cup can be modeled by the equation y equals 75 times 0.875 to the t power. And it says where y is the temperature difference and t is in minutes, okay? It says A, find the temperature of the coffee after 15 minutes. This is what I was saying. These are not very hard because, basically because they give you everything you need. They give you the equation right there. So after 15 minutes, we just plug in 15 for what? For t. Plug it in right there, and you do 75 times 0.875 to the 15th power. That gives you 10.1. But understand, that's the what? Difference, the temperature difference. So if it started out being how hot? 95 degrees, we have to do what with the 10? Subtract it, okay? So 95 degrees Celsius minus 10 degrees Celsius would be, or minus 10.1 degrees Celsius, I should say, will be 84.9 degrees after 10 minutes, okay? Again, it's getting smaller really quick. What I say? 10? My bad. After 15 minutes. Yes.
Where'd they see that? Where do you get the 10 from? I don't see that 10.
The 10 comes from right here, after we figured this out. Okay. This is what, all this equals 10. All right? Example 3.
Just a really off-topic question.
Yeah.
Why don't we use, why do we use a different system than, the rest of the world, like Fahrenheit and
I'm not
Celsius?
really sure. I guess we just started and I don't know. I'm sure there's a reason, I just don't know what it is. All right, so exponential decay and exponential growth, they both go off of this equation right here. So you need to kind of remember that one. What do these letters mean? N is how much you're going to have final, okay? N sub 0, that's your initial amount, okay? Now understand what we're doing here. We're growing or decaying. It says this is growth, which it is. 1 plus R is growth. But if you're decaying, what are you going to be doing with that R? You're going to be subtracting R, okay, if you're decaying. So, in other words, if what's in the parentheses is less than 1, right, because you're saying 1 minus something, if it's less than 1, it's going down. If it's greater than 1, you're adding R, it's going up, okay? So, we use this stuff all the time. We're back to our might question that they started out with. They said, hey, those mites, they're called varroa again, if they start out with 500, okay, the initial population is 500, they are increasing, so that's going to be growth, right? They are increasing at a rate of 14% per week. What is the expected population in 22 weeks? All we do is take the formula we just were introduced to, n equals n sub 0 times 1 plus r to the t power, and we plug in what we know. What's our initial amount? 500. So you plug that in for n sub 0. We are growing at 14%. Do not put 14. You have to change that percent to a decimal, so you put plus 0.14. And then after how many weeks? 22. That's your t. Okay? You plug it all in, you get your answer. So, that's 22 weeks. They've increased quite a bit. Okay, they went from 500 to how much? 8,930 and some change.
21, they rounded up.
Okay, they right, yeah, 0.5 or rounded up. So that's a pretty good increase in 22 weeks. What's 22 weeks, like 5 months, well, 5 or 6 months? Okay, so yeah, that's pretty quick. You use exponential functions in banking, and y'all ask me this question all the time. When are we ever going to use this? You actually will use compound interest pretty much anytime you go get a loan. Okay, they do compound interest on loans, whether you're buying a house, whether you're buying a car, whether you find a savings account that compounds your interest if you're lucky enough. Not many do. Okay. Anyway, this is the formula for it, and I want you to know it's the same formula we just talked about. Okay. They're different letters, but they're the same thing. This is going to be your A is your final amount of money you have. Okay. P is how much money you start with. It's called P because it's the principal. Okay. R is still your rate. T is still the time. The new thing here is N. N is how many times you're going to compound that interest. So,
Like
annually, yes. And it changes. So, if it says it's compounding annually, well, that just means once a year.
I've seen that.
You do this in Algebra 1. Okay? You do it in Algebra 2. So, if it says we're going to compound it annually, that means every January 1st, they take whatever money you've gained and they add it to the principal and they start over again. That makes sense? Okay? Otherwise, you're always just gaining interest on the original amount of money you put in. Okay? So if I invested $1,000 at 10%, after a year, I'm going to have $1,100. Okay? So if you're compounding it, they take that $1,100 and now you're compounding the $1,100. You're not just compounding the $1,000 anymore. Does that make sense? Okay? And you can compound it annually. Biannually means you would compound it how many times? Every 6 months, twice. Okay, if I said we're going to compound it monthly, what would N be? 12. If I said quarterly, what would N be? 4. If I said weekly, 52 weeks in a year. If I said daily, 365. I know it's 0.25, but don't put the 0.25. It's just 365. Okay. There's even ways.
Wait, Coach, would quarterly be 3 months or 4 months?
Quarterly is 4 months. I'm sorry, 3 months. Every 3 months. Yes, but it's every 3 months, but N is 4, because remember, N isn't how many months are you go by before you compound it. N is how many times you are compounding it. Okay. So we're doing it every 3 months, but there's 4 3-month sections in a year. Okay? Good question though. All right? There's even a way to compound it continuously where you're just it's being compounded all the time, and we will get to that a little later in the chapter. Okay? That involves a number that's a letter. It's going to be fun.
Wait, what?
So excited.
It's called E. E is a number, if y'all didn't know.
I'm sorry, whenever I was learning how to count, that was not a part of it.
E, I know.
1, 2, 3.
It's like an actual number, kind of like pi. Okay, pi is a number. Okay.
So what does E stand for?
E. So you're getting me off track. I know. Okay.
You can't just bring something up and then drop it.
Of course I can, but I won't. All right. So eventually, we'll get to this number called E.
D stands for
Okay. Let me see if I think it's the next chapter or the next section which we're skipping, so I'll kind of talk about it. So E is 1 plus 1 over 1. That was a bad 1 over 1.
Oh, yeah.
1 over 1 plus 1 over 2 plus 1 over 3. And you just keep, factorial. Plus 1 over 4 factorial.
Have we learned this?
What poop is a factorial?
We did it in Algebra 1.
A factorial, 5 factorial, means 5 times 4
I feel like we did this
times 3 times 2
remember
times
doing
what?
it now,
Like all the
too.
factors.
Okay? Not all the factors. All the numbers up to 5, you're multiplying them. Okay? So that's what a factorial is, and I should have put 1 on the 1 too, but 1 factorial is just 1. Okay? So 2 factorial is 2 times 1 is 2. 3 factorial, 3 times 2 times 1. 6. 4 factorial, 4 times 3 times 2 times 1. 24. And so on and so forth. Okay?
120.
So all of this, if you kept going, okay, all of this kind of adds up to 2.718 and some other decimals, okay? It doesn't ever stop. Why doesn't it ever not stop? Because we're always continually adding stuff. But what we are continually adding eventually is so small, it doesn't make a difference. Does that make sense? Because again, this bottom number just keeps getting what? The bottom number keeps getting what? Bigger and bigger and bigger, which makes the overall number smaller and smaller and smaller. Okay? So that's what E is. It's in your calculator, actually. Okay? I'm not going to pull it up.
We've
But
either done this before or you brought it up.
we have talked about E before, and we've talked about factorials before. I know if you had me, well, I don't know, the little ACT course they made y'all do, if y'all did that, you should have had the jump start. Yeah, you should have talked about factorials in
That's
it
what
a
it
little
was.
bit.
Somebody brought something
Yeah.
up that wasn't in this class and he showed it.
So, all right. So, example 4 right here. We only got 2 more. We'll be done. It says determine the amount of money in a money market account providing an annual rate of 5% compounded daily. If Marcus invested $2,000 and left it in the account for 7 years. Okay? So there's all kind of accounts you can get at the bank. You can get checking accounts. You can get savings accounts. You can get money market accounts. You can get CDs. Okay? All of these things are different ways that you're allowing the bank to borrow your money. Okay? I say all of them. They're not all allowed. Like a checking account, most banks offer free checking. Okay? But all a checking account is your hey, hold my money here, and I'm gonna get it out when I need to by paying with a check. Does that make sense? Okay. Some checking accounts cost money. Some checking accounts don't. It just depends on which account you get. Okay. Savings accounts, which are very, very, you don't get much interest. Like, I think I have a savings account, and bless his heart, it's like 0.04% interest. Now, again, 0.04%. Okay?
You get $1 million.
That's still not much. Because again, that's 0.04 what? Percent. I haven't moved the decimal yet. Okay? So it's actual, the decimal is 0.0004. That's what I'm adding to the 1. Okay? So I'm not even making a penny, really, per dollar. Does that make sense? Okay? So, it's not very good. They give you better interest rates than CDs, but CDs have different rules. A regular savings account you can kind of take out whenever you want to. A CD is called a certificate. It's basically, you can get a 6-month CD or a 12-month CD, and basically what you're telling the bank is, look, I'm going to let you borrow this money for 12 months, and I'm not going to touch it. Now, you can still take it out, but usually if you take it out, they charge you a penalty. Okay? So you just have to talk to your banker or whatever to see what you want. So if you just inherited $1,000 and you don't want to just go blow it, you want to, okay, you can say, all right, I have this $1,000. I know I'm not going to do anything with it for a year. Let me go get a CD. You're basically giving it to the bank. Hey, you redisperse this in loans and stuff, and after a year I'll come back and they'll give you this much money for letting them borrow that money. Does that make sense? Okay.
It's not, out of $1 million, you only get 400.
Yeah. See, it's not much.
Not much at all.
This is not a very good account to have. All right. So let's see how Marcus's account is going to do. Basically, all you do is plug in everything. His account is getting what? 5%. So that's your rate. That goes in right here. Okay? 5%, you change it to 0.05. We're investing $2,000. That is your principal for 7 years. Okay? That's your T. It says it's compounded what? Daily. That's where the 365 comes. Okay? And all it is plugging in, and there's how much money he made after 7 years. I take that back. That's not how much money he makes. That's how much money he has after 7 years. How much money did he make after 7 years? $838.07, basically. Okay? Because he started out, he invested $2,000, and he got out of it after 7 years, $2,838. So he made $800 just by leaving the money in the bank. Okay? Which, that's not much, but it's more than he would have made if he just would have put it in a Coke can, okay, or a coffee can and buried it in the backyard. Okay? Any questions on how to do those? It's literally just plugging into the formula and putting it in your calculator. Okay? The last one, and I don't know if I gave you any of these, but we're going to go over it just in case. Your graphing, all you need to remember is, hey, if I don't have the little line under it, it's a dotted line. See how it's dotted right here? Okay? And then, same thing as always. Less than, you shade what?
Left.
Up or down?
Oh, up or down. Oh.
Down. Greater than, I would shade up. So here I'm going to shade everything below it.
I guess I was rusty.
Okay? Any questions? Oh, there's the book's way. Their shade's a lot better than mine. Okay? Any questions? All right. You don't have much homework, but we'll see you next time. And as always, stay above the line.